Hello, in this video I'm going to show you how to develop or derive the formula for compound interest, which is this formula. The first thing we have to understand here is, let's try this example. When you invest in the bank $100 at 5% annually, what that means is that at the end of 1 year, you are going to have an additional 5% added to the initial investment of $100. In other words, you invest $100 now, 1 year later, let's say 1 year, you're going to have your initial $100 plus a 5% added to it of $100, which is 100 plus $5, which is $105. In other words, your investment, your initial investment of $100 increased by $5. Okay, simple enough. Now, remember, annually. Under this example, if you were to leave your money in the bank for less than a year, then you're going to get less than 5%, because you only get the 5% if you leave the money in the bank for 1 full year. So let's say that you leave the $100 in the bank for 6 months. Then you will not be getting the 5%. But instead, you're going to get an amount proportional to the time that you leave your money in the bank. In other words, if you leave the $100 in the bank for 6 months, then the amount of percentage that you're going to get is 1/2 of that. And why is that? Because 6 months represents or is proportional to 1/2 of 1 year. So you're going to get 1/2 of 5%. By the way, whenever you see the word "of" in math, it means multiply. So this is nothing more than 1/2 of 5%. That's what it's saying. So anyways, that's if, so you have your initial investment of $100 plus 1/2 of 5% of your $100, right? So your total amount is going to be $102.50. Okay, now the point here to understand first is that if you leave the money in the bank, say for 1 month, then we know that 1 month is proportionally equals to 1/12 of a year. So the amount of interest that you are going to get if you leave your money in the bank for 1 month, like I said, is not longer going to be the 5%. Instead, it's going to be 1/12 of 5%. So that's going to be 1/12 of 5%. Likewise, 1 day is equals to 1/365th of a year. So the amount of percentage that you're going to get is going to be 1/365 of 5%. Now, I hope I'm not losing you here. All I'm saying, and I'm giving examples for that, is that the amount of money, again, that you're getting is proportional to the time you leave your money in the bank. That's all it is. If you have trouble understand these proportions, I can make another video about that. But let's make a concrete example here. Or let's say you invest. Let's go to the next page, and then we do a concrete example. A general example. So you invest $100. That's the initial money or deposit. And we're under the condition that you're getting 5% annually, okay? We're still the same example. So after the first month, your initial investment is going to increase by the, so it's going to have $100 plus is going to increase by 1/12 of 5% of $100, right? Why? Because the new rate, in a way, if you want to think of it, it changed from 5% to this quantity, which is the same as 5 divided by 12, 5% of course. So if you want to think of it in that term, even though it is not that term, but if you want to think in that way, that the rate that it was annually 5% annually, it changed to monthly 5% divided by 12. That's going to be, this is monthly now. Okay, so that's going to be the new rate. So anyways, let's finish this that we're doing right here, this example. This becomes, we factor out the 100s because they appear on both sides of the plus sign. It becomes 1 plus 5% divided by 12. And that is after the first month. It always after. So now let's see what happens after the second month or the second compounding. And compounding just means adding, if you want to think of it that way. So now the amount of money that you have in your saving accounts change from 100 to this new amount. So now you're going to have that amount, right, in the bank. But after the second month, we're going to add interest to it, or compound interest to it, add interest to it. What is the interest that we're working with? Is this one right here, because we are on a monthly basis. So it's going to be 5% divided by 12 of, let's do a brackets here, this amount, or this quantity goes in there, which is 100, because that's the amount that you have now in the bank. It has increased your amount. And we add an interest to that new amount. So again, without breaking our heads, we can reduce this as, because we can see this quantity and this quantity are the same, we can just factor it out. And we have 100, 1. By factoring out, we just take it out, divided by 12. Big parenthesis. Obviously, this turns into 1 when we divide by the factor, the common factor. And plus, that's this plus sign right here, 5% divided by 12. Anyways, now we can see that this quantity and this quantity are the same. So we can multiply them together, and we're going to have 1 plus 5% divided by 12, and the square. So let's try one more iteration, or one more month. So let's say after the third month, we're going to have a new amount now, which is this. This is the new amount that we have in our savings account. So it's going to be 100 times 1 plus 5% divided by 12 to the second power, plus interest on that amount. And the interest hasn't changed. It's the same. It's just 5% divided by 12 times this new amount goes in there, which is 100. 1 plus 5% divided by 12. Okay, to the second power, don't forget the exponent. Because it's the same, nothing changes. The same amount just went inside the brackets. So from here we can factor out the quantity that is the same, which is this one. Factor it out. 1 plus 5% divided by 12 to the second power, obviously, parenthesis, 1 plus 5% divided by 12. All it is This quantity right here is just a common factor that is on both sides of the plus sign, of this plus sign. And this 1 comes from when we divide by the square, by the common factor. And this 5% is just the rate. And obviously we reduce this, becomes 100 times 1 plus 5% divided by 12 to the third power. We can continue, but we already see a pattern here. As a matter of fact, the pattern is when the time is 1, we see a 1 right here. When the time is 2, or the second month, we see a 2 here. And when you see a 3, you see a 3 here. So it's just patterns, right? Math is patterns. So we can say when the time equals k, a number k, we can have this quantity 100 times 1 plus 5% divided by 12 to the k, which is just following the pattern that we were talking about. Now, obviously, we didn't have to stop a month 3. We could have continued to say month 12, for example, and it would have looked like this. To the 12th power, right? And we know, because we compound them monthly, that if we compound 12 times, this quantity that I just wrote down, this one, represents 1 year. And of course, you don't have to stop there. You can continue to month 13, which would be this one, right? And it will have an exponent of, it will be the same expression right here with the exponent of the 13 power. We can continue to month 14, 15, whatever, etc., until we get, for example, let's make some space here. We can get to month 24, and it's just going to look like this. 1 plus the exponent, right? The exponent is 24. Now, just one more, for example, say month 36. We continue compounding. Month 25th, 26th, 27th, 28th, so far until you go to month 36. And it's just going to look like this. The exponent changes. We're trying to establish a pattern. That's why I keep doing this. And the pattern is this, that this represents, if we're talking about years, we can say, for example, that this is just nothing more than, we can write it down in years. It's the same expression, but instead of months, we use in years. So we can say 12 times 1 year, because we know that every 12 iterations represents a year. So in 1 year, there are 12 iterations. And 24 iterations or compoundings is 2 years. So you can write this down as 1 plus 5% divided by 12 times 12 times 2. Now, nothing has changed. The exponent is still the same. 12 times 2 is still 24, same as here. So nothing has changed. All we're doing is representing this in years. So I hope I don't get you confused here with this. So like in this one, as it is, it's okay. But if we're talking about years, we want to convert it to years. That's the reason why we're doing this. That's all it is. And you understand where that comes from. So this is 3 years, right? Now, obviously, we can have whatever numbers of years. We can have, let's say, that will be this formula. 12 times, say, t, when t represents years. Now, you can explain this formula now. You can say, well, that's my initial investment right there. That is the interest that my investment is accruing because I'm compounding monthly. And that's just the time that I have my investment in my savings accounts, accruing interest. So now you understand that, I hope. So obviously we don't have to follow, say, months. We can do days. We can do weeks. There are 52 weeks in a year. The point is, let's just do let me explain to you this before we continue. Let's say that this is a year. This line represents 1 year. That's 1 year. And we break down a year into many pieces or segments of same length. So if there are 12 segments in here of equals length, you know that that represents 1 month. Each segment represents a month because there are 12 segments or 12 months in a year. Likewise, you can break it down into 365 segments of equals length, and you know that each segment represents a day because there are 365 days in a year. Although, just a bank will use 360 segments like this in 1 year. And the reason why they do that, we know that in 1 year, there are 365 days. But the bank would say that in 1 year, there are 360 days because they say that each month, regardless, like February has fewer days than, say, January. For example, January has 31 days. So they can say that each month has exactly 30 days. And this is the answer or the reason why banks use this, why they break a year into 360 intervals of equals length. Anyways, we can cut a year into n pieces, where n can represent months, weeks, days, hours, minutes, seconds, doesn't matter. That's what we're breaking down a year into. And you can represent that mathematically by saying each segment's length is equals to 1 over n. So that when you add all the segments, right, this segment is 1 over n, this is 1 over n, and so forth, however many they are, when you add them up all, you get 1. You get, if you add 1 plus 1, like 1 over n plus, and so forth, n times, you get 1. All it is that when you compound n times, you obtain 1 year. I hope I'm not losing you here. It makes sense, doesn't it? If you break a year into n segments, and then you add them up, the n segments, you're going to have 1 year. You just broke it down and put them together, you have 1 year. Not a big deal. Okay, fine. But we saw earlier that if you get an interest annually of R%, that's the interest, R% annually. Now, don't get confused with, say, R% or R. As long as you understand that the number, whether it be this one or this one, just remember which one you're working with. I would choose decimal form because you want to reduce the quantity, but regardless, just keep in mind which one you're working with. That's all, not a big deal. So if R is the interest given annually, as we're talking about right here, that's okay if you leave your money in the bank for 1 year. You're going to get R% in your investment. However, if you leave your money in the bank for less than a year, as we said earlier, the amount of interest your investment is going to accrue is going to be proportional to the time you leave your money in the bank. So we know that in the case where a year was broken into n pieces, we can say that the proportion is 1 over n. 1 over n represents the proportion of a year. And so the interest that's going to be added to your initial investment is going to be 1 over n of R, which is nothing more than R over n. And if you have trouble kind of understanding this, you can substitute it like in the example that we did earlier with R represents 5% and then represents 12 months, just so you can understand it. But if you do, we can proceed further. We can say, as we did earlier with the 100, we can say, well, on the first, initially I have an investment of P, which means present value. That's what the P stands for usually in the formula. So after the first compounding or the first cycle, you're going to have your initial investment plus interest added to that initial investment, which is going to be R over N. And so we can reduce this as common factor. It's just the P, 1 plus R over N. Now, obviously, after the second compounding, we are going to have now your investment, it increased by this amount, right? That's the new amount that you have. However, after the second compounding, we're going to accrue or add interest to that amount. So add interest, which is not changing, to that amount. And so we can factor this out. The common factor is P parentheses 1 plus R over N. And inside the parentheses, we're going to have 1 plus R over N, right? The common factor is this guy. So we factor it out. And here it is outside. That's what it means. That's the R over N. And the 1 just comes from dividing by the common factor. So anyways, now we can reduce this further as this to the second power because this quantity and this quantity are the same, and so when they multiply them together, it becomes square. Simple. Let's just see one more iteration. Say after the third compounding, the new quantity that we have is this. Plus interest, right? That's that new quantity. Plus interest added to the quantity. Let me explain. This is the quantity, or that one, however you want to see it. We just add an interest to it. So it becomes, factor out the common factor, which is, this is the common factor, parentheses, 1 plus, easy. It seems like it's always 1 plus R over N in the parentheses, right? And it is right, that's what it is. So that's P1 plus R over N to the third power. Anyways, the pattern that we're seeing here is the frequency of compoundings matches the exponent. In other words, we can have, when the time equals k again, we can have this formula or this result. Now, from here, we can reduce this to this formula, or this is P. N times T. And why is that? Because remember that in 1 year, one year was broken into n segments. So every year is going to be, is going to have n segments. So if you have 1 year, you're going to multiply it by 1 because you have n segments or n compoundings in 1 year. And in 2 years, you're going to have twice as many. So you're going to multiply it by 2. I hope I'm not losing you here, but you can, if you want to see how this works out, you can work this out with months and don't stop when you get to the 12th month. Continue until you get the 24 month, 36 months, and you see you multiply the exponent every time you complete a cycle of 12. When talking about monthly, you're going to multiply by by 12, right? Likewise, that's the reason why we multiply it by t. Not a biggie. So we can say they use the formula A, which means accrue or aggregated total equals to the principal initial investment, right? 1 plus R over N, where N stands for the number of segments that you cut a year into, to the N times T. And that's pretty much the formula. I mean, questions? Another way to derive this formula really quick is using something called the difference equations. Just really quick here. I mean, I think, I don't know if I'm convinced that you understand how the exponent came out. I could make another video about it. Or for now, you can go back to the example where we did the monthly, how I say don't stop when you get to month 12. You can continue to month 26, month 36. And if you understand that, I believe that you can understand how this exponent n times t comes. So a difference equation will be something like this. Rho y sub n plus b. Doesn't have to be positive. All it is, for our purpose, we're gonna cancel. We're gonna make this 0. And by the way, the initial value is just initial, like that. Bear with me here. Think about it. The first iteration would be equals to rho, following this pattern. So if this is 1, this will be minus 1, which is y sub 0. Okay, this one I made is 0. We're not concerned about the b. So the second iteration would just be rho y sub 1. The index reduces by 1, which we already know what y sub 1 is, right? It's just rho parenthesis. If you want, we're going to write down the value of y sub 1, which is rho y sub 0, which is rho square y sub 0. You can see the pattern already. I mean, the square matches the index of the y. But anyways, y sub 3 will be rho. That's the letter P, I guess. Y sub 2, which is rho parenthesis. What's y sub 2? Y sub 2 is up here, right? Which is p squared, y naught. P sub square, y naught, which is just p cubed, y sub naught. All I'm saying here is just a difference equation. It's just giving you another way to derive the compounding formula. And you can continue to when it's n, which in reduced form is going to be rho or p to the n y sub 0. And rho is actually equals to 1 plus, we can derive it as n over n, the constant factor, which represents the interest. So if you substitute it here, if you want, you can say this is a balance, represents balance, 1 plus r over n. This is the initial, right? The initial investment, if you want to think about it. So you can substitute it by p. But most important than that is the if you look at it, it just looked at like this formula. Oh, I apologize here. There's an exponent. 1 plus r over n, then the initial investment. Anyways, that was just a side note, I guess. The thing is this. If you understand this, I think I've done my job. I'm going to do more videos. I'm going to do more videos about this, but I think for now that's fine.